Hello students. So today we will explore chapter 9 hydrocarbon, in which we will cover the theory part 3, where we are going to discuss the NCERT section 9.2.2 and 9.2.3. So this is our disclaimer. Now in this lecture our learning objective would be to look after, first of all, the various methods for preparation of alkanes. So we have known a lot about alkanes in the previous classes regarding the nomenclature, isomerism and the homologous series and all. Today we'll discuss the preparation as well as explain and relate the physical properties of alkanes. Now, if I talk about the specific names of the NCERT section, then it would be 9.2.2, which is preparation of alkanes. Then 9.2.3 section, which is properties of alkane, specifically the physical properties. After that, we will summarize our today's lecture with a short note. So let's now discuss the method of preparation for alkanes, beginning with the unsaturated hydrocarbon. So these are hydrocarbon that contain double or triple bond. The process of converting this into alkanes involves breaking this multiple bond to form single bond, which is crucial for creating saturated hydrocarbon. The first method we will discuss in this is hydrogenation. This process involves adding hydrogen to unsaturated hydrocarbons, effectively saturating them. It is a common industrial method used to convert vegetable oil into margarine, for example. Next, we have alkyl halides. So these are compounds which are attached to a halogen atom, and they serve as a starting point for preparing alkanes through various reduction reactions. One such reduction method involves using zinc and hydrochloric acid, known as the zinc/HCl reduction. So this method is effective in removing the halogen atom and replacing it with hydrogen, thus forming an alkane. Another important method is the Woods reaction. So this involves coupling of two alkyl halides in the presence of sodium metal, resulting in the formation of a longer alkane chain. It is useful for synthesizing higher alkanes. Moving on to the carboxylic acid. So these are organic acids characterized by the presence of a carboxyl group. They can also be used to prepare alkanes through specific reactions. The decarboxylation reaction is one way to convert your carboxylic acid into alkanes. So this involves the removal of a carboxyl group, releasing carbon dioxide and forming an alkane. Lastly, we have coal-based electrolysis, a method that uses electrochemical reactions to decarboxylate carboxylic acids, resulting in the formation of alkanes. So this method is particularly used for synthesizing symmetrical alkanes. Now, let us dive into the first method, hydrogenation of unsaturated hydrocarbon, also known as hydrogenation. This process involves a chemical reaction where alkenes or alkynes are converted into alkanes. It is a fundamental reaction in organic chemistry that helps us to understand how we can manipulate hydrocarbon structure. In this reaction, alkanes or alkynes react with hydrogen gas, denoted as H2. So this reaction requires the presence of finely divided catalysts such as platinum Pt, palladium Pd, or nickel Ni. So these catalysts are crucial as they facilitate by the reaction by lowering the activation energy, making the process more efficient. This hydrogenation process is also known as Sabatier-Sanderson reaction, named after the chemists who developed it. So this reaction is a classical example of catalytic reduction and hydrogenation and is widely used in both industrial and laboratory settings. So we will now look at specific example where we convert an alkene to an alkane. So this transformation is a key application of hydrogenation, where we take an unsaturated hydrocarbon and make it saturated by adding hydrogen atoms to it. So here is a specific reaction. Ethene, which is an alkene, reacts with hydrogen gas in the presence of a catalyst such as platinum, palladium or nickel to form ethane and alkane. Note here hydrogen is added across the double bonded carbon, and since it is also known as reduction. Now continuing the preparation of alkane from unsaturated hydrocarbon. Let us start with conversion of an alkyne to an alkane. Using ethine as an example, when ethine is a simple alkyne which reacts with hydrogen gas in the presence of catalysts like platinum, palladium or nickel to form ethane, a saturated hydrocarbon. So this reaction is crucial because it demonstrates how we can saturate hydrocarbon by adding hydrogen. Now let's look at another example with propine. So when propine reacts with hydrogen gas, again using a catalyst such as platinum, palladium or nickel, it forms your propane. So this is NCERT equation 9.3. Continuing with the preparation of alkanes from unsaturated hydrocarbon, let us now begin by understanding the mechanism of hydrogenation. Metals like platinum, palladium and nickel plays a crucial role here. They absorb hydrogen gas on their surface, which weakens the hydrogen bond. So this is an essential step because it prepares the hydrogen for the next stage of the reaction. Now with the hydrogen activated, it can add to the unsaturated carbon atom. So this is a key part of the hydrogenation process where the double bond or triple bond in unsaturated hydrocarbon are converted into single bond forming alkanes. So this transformation is what makes hydrogenation so valuable in organic chemistry. To help visualize this process, here is an image illustrating the hydrogenation mechanism. Notice how the hydrogen atoms are added to the carbon atoms, converting the unsaturated hydrocarbon into alkane. So this is your image. Let us talk about the reaction condition. So what are the reaction conditions? It is important to note that if we use platinum or palladium, then the reaction may work well at the room temperature, but with nickel we have to provide high temperature for the reaction to happen. Okay, so this is the important reaction condition that you should remember. What? That platinum and palladium, they work at room temperature, whereas nickel, it requires high temperature and pressure. Now we will see how can we prepare alkanes from alkyl halides. Let us start by understanding the reaction process. Alkyl halides, except for fluorides, can be reduced to alkanes using zinc and dilute hydrochloric acid. So this is a key reaction because it provides a straightforward method to obtain alkanes from more reactive halides. Now we will look at the general equation for this reaction. So this equation will help us to understand the transformation that occurs during the reduction process. Here is the general equation. So Rx plus H2 giving us RH plus HX, where Rx represents the alkyl halide and RH is the resulting alkane. Zinc and H plus act as the reducing agent and facilitating the conversion of halide to an alkane. Next, let us consider a specific example to illustrate this reaction. We will see how chloromethane is converted into methane, which will help solidify our understanding of the process. In this example, chloromethane reacts with hydrogen gas in the presence of zinc and H plus to form methane and hydrochloric acid, which is HCl. Another example involves chloroethane. When chloroethane reacts with hydrogen, it forms ethane and hydrochloric acid. Finally, let us look at the reduction of 1-chloropropane to propane. All these reactions highlights how the method can be applied to different alkyl halides to produce various alkanes. So this concludes our 3 examples: methane, ethane and propane preparation. Now let us learn about some more preparation methods of alkanes from alkyl halides. So we are going to discuss about the Wurtz reaction. Starting by introducing the Wurtz reaction. So this reaction involves alkyl halides reacting with sodium metal in dry ether. So it is crucial to note that ether must be free from moisture to ensure the reaction proceeds correctly. So this step is used to create higher alkanes. This setup is used to create higher alkanes. An important setup except of this Wurtz reaction is that it is typically used to prepare alkanes with an even number of carbon atoms. So this is due to the coupling of two identical alkyl groups, which we will explore with further examples. Note, now let's look at the general equation for the Wurtz reaction. So this equation will show us how two alkyl halide molecule will react with sodium to form an alkane and sodium halide. Understand this equation is important to predict the product of the reaction. So here is the reaction. 2Rx plus 2Na in the presence of dry ether is giving us RR and 2NaX. So when we can take specific example to explain the same. So what is the specific example? We are taking bromomethane. In the presence of sodium and dry ether, the two molecules of bromomethane will couple with each other, forming ethane. Notice how the number of carbon atom is doubled from reactant onto the product. Along with this, we are also getting sodium bromide. Next, we can take the example of bromoethane. Again, in the presence of sodium and dry ether, it will give you double the number of carbon present in the reactant side. So on the reactant side, we have 2 carbon. So we will get a total of 4 carbon in a linearly fashion way, giving us N-butane, and again we will get the side product as sodium bromide. Remember, I have told you this dry ether is there to prevent sodium from reacting with the environment, because sodium is a very reactive metal. It even reacts with the environmental oxygen and starts burning. So this is a very exothermic reaction. To prevent that, we are doing our reaction in a non-polar solvent such as dry ether. Now let's learn more about this Woods reaction. For that, let's start with the intramolecular Woods reaction. So this type of reaction occurs within a single molecule, leading to the formation of a cyclic alkanes in most of the cases. It is fascinating because it allows us to create complex ring structure from simpler linear molecules. Pay attention to how the reaction progresses with the molecule itself. Now, compounds that contain more than one halogen atom can undergo this intramolecular Woods reaction. So this is significant because it enables the formation of cyclic compounds. So this is the first case we are seeing the formation of a cyclic alkane. So the cyclic alkanes are prevalent in many natural and synthetic material. Think of it as the molecule folding in on itself to create a ring. Here is a visual representation of the intramolecular Woods reaction. Notice how the halogen atom present at the terminal end facilitates the formation of a cyclic structure. Now, we are getting a 5-membered ring because both of this bromine is getting eliminated, this, and they are joined by the ends to give us the cyclopentane. Again, this reaction is occurring in the presence of sodium and dry ether. Next, when both intramolecular and intermolecular coupling is possible, the intramolecular product is much more preferred. Okay, so this preference is due to the stability and lower energy requirement for forming cyclic structure. So basically, it is like choosing the path of least resistance, resulting in a more stable and energetically favorable product. Now, we will learn about some more Woods reactions. Let's start by discussing the limitations of the Woods reaction. So it is important to note that this method can result in a mixture of alkane when different alkyl halides are used. This can complicate the purification process and affect the yield of the desired product. So, for example, when using different alkyl halides such as methyl iodide and ethyl iodide, the reaction can produce a mixture of alkane. Now, this is a key limitation to keep in mind when planning synthesis using the Woods reaction. Here is a specific example. So when methyl iodide react with sodium and ethyl iodide in dry ether, propane is formed along with the sodium iodide. So this equation illustrates how the reaction proceeds and highlights the formation of a new carbon-carbon bond. Now there are more possibilities in this reaction. We can also get a ethane by reaction of 2 molecules of iodomethane, right? Or we can also get a butane by the reaction of 2 moles of iodoethane, right? So next we are seeing this only. So when 2 molecules of methyl iodide react with sodium in dry ether, ethane can also be produced. So this example shows the simplicity of forming a straight chain when identical alkyls are used. Now, as I said there can be also one more possible reaction where 2 molecules of iodoethane can react to form a butane along with sodium iodide. So these 3 products are possible if we are taking a mixture of 2 different alkyl halides. However, it is crucial to understand that methane cannot be produced using the Woods reaction. This is because reaction involves coupling two alkyl halides, and methane having only one carbon atom cannot be formed using this process. After that, the Woods reaction is essentially a coupling reaction, meaning it joins two alkyl groups together. This is why it is effective for creating longer carbon chains but not suitable for synthesizing methane. Since methane consists of only one carbon atom, it lacks the necessary structure to participate in a coupling reaction. So this limitation is inherent to the nature of the Woods reaction. To summarize, two carbon chains can be joined together to create a molecule with only one carbon atom, such as methane. This is a fundamental limitation of Woods reaction that must be considered when planning synthesis route. Now let us discuss about the limitations of Woods reaction further. Now the next one is the preparation of tertiary alkyl halide in Woods reaction. So these compounds do not undergo the Woods reaction efficiently. This is an important point because it highlights the selectivity of reaction based on the structure of alkyl halides. When tertiary alkyl halides are used, the reaction tends to leading to the elimination rather than coupling. This means that instead of forming the desired alkane, the reaction results in the removal of hydrogen halide, leading to an alkene formation. So this is a classical example of how a reaction condition can influence the outcome. To summarize, the Woods reaction is not suitable for tertiary alkyl halides due to the tendency for elimination reaction, and it is also not suitable for the preparation of methane. Okay, methane, right? And we cannot take two different kind of alkyl halide to form a third type of alkane. So your alkane can only be formed if it is containing an even number of carbon, not the odd number. Now let us discuss the another method. So here we will see the preparation of alkanes from carboxylic acids, also known as decarboxylation. So let us look at the reaction in detail. When sodium salt of carboxylic acids are treated with mixture of sodium hydroxide and calcium oxide, known as soda lime, they produce alkanes with one less carbon atom. So this is a key transformation because it allows us to simplify the carbon chain. The reaction can be represented as RCOONA in the solid form reacts with NaOH in the solid form to give us RH in the gaseous form plus Na2CO3 in the solid form in the presence of calcium oxide. Notice the carboxylic group is replaced by a hydrogen atom, resulting in the formation of an alkane. So to illustrate this reaction, consider sodium ethanoate, which is a sodium salt of acetic acid. When it undergoes decarboxylation, it produces methane, the simplest alkane. The reaction is CH3COONA NaOH, giving us CH4 and Na2CO3. This example highlights that decarboxylation can be used to generate alkanes from carboxylic acid, and we can also prepare methane irrespective of the previous method, which was not suitable for creating methane. Then we will now learn about the preparation of alkane from carboxylic acid. So we'll do some more examples on this. So decarboxylation of carboxylic acids often requires the stabilization of the intermediate carboanion. So this is very, very important. So in some cases, if you are not forming the sodium salt, then in that case you can directly decarboxylate, but first you have to find such a substrate where the carboanion can be stabilized. You can see that after removal of this COOH, the negative charge goes on a carbon which is next to the carbonyl carbon. Now here your carbonyl carbon and your negative charge can be under resonance, right? You can see that a second resonating structure is possible for that. And this stabilization of the negative charge allows the decarboxylation directly without forming the sodium salt. Is it clear? So decarboxylation of sodium salt of carboxylic acid with soda lime does not require this stabilization. So if you are forming the sodium salt, then you don't need this stabilization. But if you are forming it without this sodium salt, you need to stabilize the negative charge on the next carbon, which is after your carboxylic acid group. Now let us do a problem. The question asks us that sodium salt of which acid will be needed for the preparation of propane. Write the chemical equation for the reaction. Now you are given some time Just solve it by yourself. It's an easy one. Meanwhile, I will move on to the solution. So, I hope you have solved it. You have to decide that what is the sodium salt which is needed to prepare propane, and you have to also write the chemical equation for that reaction. To start, remember that alkanes can be synthesized through the decarboxylation of sodium salt of carboxylic acid. So this is a key method in organic chemistry for preparing alkanes. In this process, the sodium salt of carboxylic acid is heated with soda lime, which is a mixture of sodium hydroxide NaOH and calcium oxide CaO. This reaction removes one carbon atom as carbon dioxide, which is crucial for understanding how the carbon chain is shortened. The product of this reaction is an alkane with one fewer carbon atom than the original carboxylic acid, and it is an important concept because it helps us to predict the resulting alkane based on the starting acid. So, propane, the alkane which we want to prepare, contains 3 carbon atoms. This information helps us to determine the number of carbon atoms needed in the starting carboxylic acid. So, what it should be? So, since decarboxylation removes one carbon atom, the carboxylic acid with which we are starting must have 4 carbon atoms. So, this deduction is essential for selecting the correct acid. Now, the sodium salt of butanoic acid, which has 4 carbon atoms, when it is undergoing decarboxylation, what it will produce? It will produce propane because one carbon will be reduced from it. You can see this same in the given chemical equation. So, the sodium salt of butanoic acid reacts with sodium hydroxide in the presence of calcium oxide to produce propane and sodium carbonate. So, this equation visually represents the carboxylation process, decarboxylation process. Now, let us discuss about the coal-based electrolysis. So, this is also a type of preparation of alkane from carboxylic acid. Here, in coal-based electrolytic method, we perform electrolysis on an aqueous solution of sodium or potassium salts of carboxylic acid. So, this process results in the formation of alkane at the anode. It is important to note that this method not only produces alkanes but also releases gases like carbon dioxide and hydrogen, which can be useful in other chemical processes as well. Here is the example for the same. So, you can see a chemical equation where your 2 moles of acetate ion, which is a sodium salt, is reacting with water. So, you can say it is going under electrolysis and it is producing ethane, carbon dioxide, hydrogen and 2 moles of sodium hydroxide. So, this equation shows the transformation of sodium ethanoate into ethane along with the byproducts. Now, this reaction is known as coal-based electrolytic method. Named reaction like this one is essential in organic chemistry because questions are asked from here as they are standard method preparatory method for alkanes. Now, let us learn about the coal-based electrolytic method in detail regarding its mechanism. Starting by the mechanism. So, this process involves the electrolysis of the salt of carboxylic acid. The key here is that the carboxylate ions are decomposed at the electrodes, leading to the formation of alkanes. Next, we will focus on what happens at the anode during this process, and at the anode what will happen? The carboxylate ion loses electrons, which is a process known as oxidation. So, this is crucial because it leads to the formation of radical that eventually combines to form alkanes. So, here you can see that same thing. Your acetate ion is removing 2 electrons, so it is undergoing oxidation and forming the acetate free radical. Along with this, we are also getting the methyl radical and 2 moles of carbon dioxide. Then 2 moles of this methyl radical can combine together to form a ethane molecule, which was our desired product. What must be happening at the cathode? So, at the cathode, reduction occurs where electrons are gained. So, this part of the process is equally important as it is complementing the oxidation process and which is happening at the anode. Here is an image to show the reaction at the cathode. Notice how the ions gains electron, which is an hallmark for the reduction. So, you can see the H2O is gaining the electron, and what it is forming? It is forming OH and H radical. Now, 2 H radical can combine together and form the H2 gas. Again, this method also has a limitation. Methane can also not be prepared using this method. So you cannot prepare methane by using Kolbe electrolytic method or Wood's reaction, because in both of the reaction, a coupling type of reaction is going on. So two alkyl groups are combining together to form a single alkyl chain. Now we will move on to the physical properties of alkane. The first one that we will talk about is polarity and solubility. So they are interrelated. Therefore, we will talk about them in a pair. After that, we will see the boiling point. So let us discuss them in detail. Starting by the first physical property, which is polarity and solubility. So alkanes are almost non-polar. This is because the electronegativity difference between the carbon and hydrogen is minimal, and it is resulting in covalent CC and CH bond. So this non-polarity affects how alkanes interact with other substances. The intermolecular force in alkanes that are only present are van der Waals force. So these are weak forces that occurs between molecules, which is why alkanes have relatively low boiling and melting point compared to the polar compounds. Now let us look at the physical state of alkane at room temperature, which is 298 Kelvin. So this was help us to understand how their molecular size affects their state. If I talk about from C1 to C4, such as methane and butane, so they are gases at room temperature. This is due to their small size and weak van der Waals forces. After that, as the carbon chain length increases, alkanes goes from C5 to C17, then they become liquid. This is because the van der Waals force becomes stronger with longer carbon chains requiring more energy to change their state. Alkanes with 18 or more carbon atom are solids at room temperature. So the increased molecular size leads to even stronger van der Waals forces, making them solidify. Regardless of their state, all alkanes are colorless and odorless. So this is a characteristic property of all alkanes. Now, it helps you to distinguish between alkanes and other organic compounds. Finally, alkanes are soluble in non-polar solvent, but insoluble in polar solvents like water. This is due to the common line, which is like dissolves in like principle, where non-polar substances dissolve in non-polar solvents. Now let us discuss about the second physical property, that is boiling point. Starting with the molar mass, as the molar mass of the alkane increases, their boiling point also increases. This is because larger molecules have a stronger van der Waals force, which require more energy to overcome. Think of it like trying to separate two magnets. The stronger the attraction gate, the more effect it takes. Now consider branching in alkane. So branched alkanes have lower boiling point compared to the straight chain counterparts. This is due to the reduced surface area for intermolecular contact, which weakens the van der Waals forces. Imagine trying to stack irregularly shaped blocks. They don't fit together as snugly as uniform ones. To summarize this, the boiling point of alkanes is influenced by both molar mass and molecular structure. Larger molecules and straight chains generally have higher boiling point due to strong intermolecular forces like van der Waals force. Now let us try to understand boiling point trends in butane isomers. Here is an image for that. What you can see, that the normal butane, N-butane, is having a boiling point of 273 Kelvin. Now you take the same number of carbon and same number of hydrogen, means you are not changing the molar mass, but you are changing the structure. So you are trying to draw a different structural isomer for N-butane. For that, we are branching one of the straight carbon onto the onto the longest chain in the middle carbon, right? So that will create 2-methyl propane. As a result of this branching, the boiling point of the given compound has decreased. So it has gone from 273 Kelvin to 261 Kelvin. So you can say that with increase in branching, the surface area of the given molecule decreases, and hence the boiling point decreases because of the decreased van der Waals force. Now let us try to understand boiling point trends in pentane isomer. So here you can have 3 isomers of pentane. The first one is a straight chain. Now we branch one of the branches on the straight chain. Then after we branch 2 substituent. This increased branching is decreasing your boiling point. You can see here very quickly. So we have 300 and 9 Kelvin for normal pentane. Then for isopentane it is 301 Kelvin, and for neopentane it is 282.5 Kelvin. So again, due to the decreased surface area, the van der Waals force has decreased and the boiling point has decreased at the same time. Let us now summarize our today's lecture. So we started with the methods of preparing alkanes. So the first method was from unsaturated hydrocarbon. So this was done using hydrogen gas with platinum, palladium or nickel catalyst, where platinum and palladium requires room temperature and nickel requires high temperature and high pressure. After that, it can convert alkenes and alkynes both to alkanes. So this was the first method. Next is from alkyl halides. Here also we can do the reduction using zinc in the presence of acid like HCl. Next, we have Wood's reaction. So it is used for again the alkyl halides, and this reaction occurs in the presence of diether with sodium. So this reaction has a limitation. It is only there to form primary and secondary. It is only applicable to primary and secondary halides and not to tertiary one, because tertiary can undergo reduction. Similarly, it cannot be used to prepare methane because it is a coupling reaction. It will at least produce 2-member long chain. Further, if you are using two different alkyl halides, it can give you a mixture of different alkyl halides. So you cannot prepare a hydrocarbon properly if it is containing an odd number of carbon. You will get a mixture, right? Then moving on to the next preparation methods. So next is from the carboxylic acid. How do we do it? So we can do the decarboxylation with the soda lime, which is NaOH and CaO. So if you heat it with NaOH and CaO, what will happen? The decarboxylation will take place and you will get your alkane. Remember, it can be used to prepare methane, where you can use sodium ethanoate. Lastly, we talked about the coal-based electrolysis. So in coal-based electrolysis, we are doing the electrolysis of the sodium salt. Remember, it cannot be used again to prepare the methane, and it is also a coupling reaction. Remember, the number of carbon in the required product should be only even. Last, we talked about this physical properties. So first was about polarity and solubility. So you know that alkanes are non-polar compound because the difference between carbon and hydrogen is not that much significant. So as a result of this non-polarity, they are only soluble in non-polar solvent because like dissolves in like. So you cannot dissolve your given alkane in water efficiently. Okay, at some point it would be soluble due to large van der Waals force, but it is not soluble. It is kind of very less soluble. If I talk about their state, so C1 to C4 are gases due to this weak intermolecular force. Then C5 to C17 are liquids, and the compounds having carbon count greater than 18 are solids. Next, we talked about the boiling point. So boiling point increases with the molecular mass. So this is absolutely occurring due to the increase in surface area and stronger van der Waals force in larger molecules. Interestingly, hydrocarbon with branched chain have lower boiling point than their straight chain. So this is because branching reduces the surface area available for the intermolecular forces. The more branching a hydrocarbon has, the lower is its boiling point. This is an important concept because it affects how the hydrocarbons are used in different applications. The reason for the lower boiling point in branched hydrocarbon is the reduced surface area for van der Waals forces. This means less energy is needed to separate the molecule. This was all for today's lecture. I hope you enjoyed it. Thank you for joining the session.